All right, where we had left off in chapter 18, we had looked at some reactions, and all the reactions that we had looked at were basically ways to make ketones, and all of them had been reactions that we had saw before. So now we're going to look at some new reactions to make ketones, and then we're going to look at aldehydes, and then we're going to look at some reactions of the ketones and aldehydes. So this is not anything different. It's just stuff that you have not seen before. So the first thing we're going to look at is on part 2, we're going to look at how to turn a carboxylic acid into a ketone. So if I look at a carboxylic acid, now as I go through this, the key thing is to understand this reactant goes to this product, but the mechanism oftentimes helps you when you take the test to make sure you keep the groups where they belong. So if we were to take this and just treat it with a base, now we're going to use lithium hydroxide here because we're going to see in a second why we're using lithium hydroxide instead of sodium hydroxide. This is just a base. This is an acid. So all this does is deprotonates the carboxylic acid. Okay? Now, if we wanted to, we could write water and the lithium ion out here. I normally do not write those whenever I do these reactions. I don't write the counter ions, but if you want to write the counter ion out there, you can. Okay? So let's go ahead and do it for now. I normally do not write that, but again, it's there. Now we're going to treat that with a lithium reagent. Now we're going to use a lithium reagent here instead of a Grignard reagent because lithium reagents react better with carboxylic acids. The reason we had to unprotonate this or deprotonate this carboxylic acid is, remember, lithium reagents are destroyed by acidic hydrogens. So the first step was to get rid of the acidic hydrogen. The reason we chose lithium hydroxide here was because now we're going to add a lithium reagent. And that makes all of our counter ions in solution lithium atoms. We don't want a mixture of lithium atoms and sodium atoms and so forth and so on. So that's why we chose lithium hydroxide. Now, if you remember, this Grignard reagent is nothing more than a negative R and a positive lithium, okay? Notice I'm using R prime because this R group does not have to be the same as this R group. So again, just like before, this is going to backside attack, kicking that pair of electrons out. Now notice that the product that this gives, and I'm going to write it down here, just keeping track of things, we've got the carbon. Now notice both oxygens now have an extra lone pair, so we have a -2 ion. Notice we get an R prime down here. Okay, so all that happened was the R prime came in backside attacked and kicked the oxygen up. Now if we acidify that, so we're just going to add some acid, we could simply add water. That would be a strong enough acid to do this. Notice what I get out of this. I get an OH attached here, an OH attached here, and the R prime. And we've talked about this several times before. When you have a compound that has 2 OHs attached to the same carbon, what normally happens is one of these waters leaves. Now I'm going to rewrite this like this. But isn't that the same thing as this? So what's the overall result? And this is what you would have on your note card. The carboxylic acid, step 1, adding lithium hydroxide. Step 2, adding a lithium reagent. And step 3, acidifying. What does that yield for me? A ketone. Okay? So notice what happens. We can turn a carboxylic acid into a ketone. We didn't know how to do that before. Now, if we think about this, we know how to take a carboxylic acid and do lots of things with it. We know how to put a carboxylic acid group on an aromatic ring. Now we can take that same carboxylic acid and turn it into a ketone. So that gives us another route to make compounds. So the overall result of this is the carboxylic acid becomes a ketone. Now, some of y'all are going to say the overall result of this is the OH gets replaced by an R prime group. And that's the same thing. Notice it's exactly the same reaction. So again, these reactions are not magic. They make perfect sense. Now let's look at another reaction. This is a nitrile reacting with a Grignard reagent. Now, if we think about a nitrile, it's a C triple bond N. Now, if we react this with a Grignard reagent, again, remember this Grignard reagent is just a negative R and a positive magnesium. So where is the R going to attack? It's going to attack the C, because that negative R is going to be attracted to that positive C, kicking out this pair of electrons. Now watch what that does for me. I still have a double bond on the carbon and an R prime now attached to the carbon. If I look at the charges, this nitrogen would now be negative. Now, if I wanted to write my counter ion out here, I could write my MgX as the counter ion. Sometimes I do that, sometimes I don't. Okay, it's just an ionic bond. Okay, now if I acidify this and add acid, now I can write the acid as H plus. I think in my notes here I wrote it as H3O plus. What that does for me is this. It protonates the nitrogen. Okay, now after several steps, we're going to get the ketone. Now, you're not going to be responsible for these steps. So over here somewhere, what happens is the N double bond H gets changed to a C double bond O. So the overall result is that if you take a nitrile and add a Grignard reagent in step 1, followed by protonation in step 2, this becomes this. Now, I want to show you the steps to go from here to here. And I'm going to show you these steps, not because you need to know them on the test, but because you're going to see this kind of thing oftentimes whenever you're talking about biological chemistry. A lot of biological chemistry is nothing but protonation, deprotonation, protonation, deprotonation, and many reactions occur. So when you're looking at the biological mechanisms for how molecules are reacting in the body, the overall result may be that this becomes this. But the mechanism of how this becomes this is something that oftentimes students don't see. So let me show you what's going to happen here. So, excuse me, we protonated to go from here to here. Now let's see what else we can do. We can take this and we can protonate again. So watch what happens. R, C, R prime, N, H, H with a double bond. Now the N becomes positive. Now watch what happens next. Because it's in acidic solution, we're going to add water. Now the water, remember, has lone pairs on the oxygen. So where would that water attack? Since the oxygen is partially negative, it's going to attack the carbon, kicking out that pair of electrons. Okay, so now let me redraw that. Okay, so now we have R, C, R prime, N with two H's on it. Okay, and a lone pair now, because notice the lone pair went to the nitrogen with a water attached up here. Now, if we notice this, now the water is protonated. That's where my positive charge is. Now, I'm going to have to erase some of this stuff, so let me just erase this now. Again, not having much of a blackboard space makes this a little bit hard to show these long mechanisms. Then another water comes in here. Now, what this water is going to do is we're going to deprotonate this. So it's going to come in here and pull off one of those hydrogens. Now notice what this product now looks like. R, C, O, H, R prime, N, H, H with a lone pair. Two lone pairs on that oxygen. Now, because it's in acidic solution, we can reprotonate this. But instead of reprotonating on the oxygen, we're going to reprotonate the nitrogen. So we're going to add acid to it, and notice what I'm going to get. Now, I know this is not exciting at all, but it's important for you to see this at least once. So we reprotonate that nitrogen. Now this positive charge is there. Now watch what can happen. This pair of electrons can come down to form a double bond, kicking off the ammonia molecule. The ammonia molecule then gets protonated in the acidic solution, but notice what we now have as their organic compound. R, C, R prime, double bonded O, still hooked to an H with a positive charge. And then water comes in and deprotonates that, and notice we get the ketone. So to go from here to here is nothing but protonations and deprotonations over and over again. So whenever you start looking at biological reactions and you say, how can this biological function group, a C double bond N, get changed to a C double bond O in some kind of biological reaction? Notice it's nothing more than a protonation step followed by deprotonation over and over again. And again, it's not magic, okay? You're not going to be responsible for all those protonation, deprotonation steps in this class on any mechanism. I'm going to ask you, what's the mechanism to take for this entire reaction? I'm not going to do that. But again, if you ever have to do that, now you've seen an example where that kind of thing occurs. Now what we're going to do is look at some more reactions. The next reaction is we're going to take and make an aldehyde or a ketone from an acid chloride. If we take a carboxylic acid and treat it with this compound, SOCl2, that compound's name is thionyl chloride. What it does is simply does this. it takes the carboxylic acid, and turns it into an acid chloride. Okay? You need to know that reaction. But one of the nice things about an acid chloride is we can treat it with lithium aluminum hydride. And it takes the acid chloride and turns it into an alcohol. So notice this is a reaction. These two reagents together can turn a carboxylic acid into an alcohol. That's a reduction, because notice what we've done. We've removed one oxygen and added two hydrogens. But this reaction is even much more important. If we take this acid chloride and treat it with this special reducing agent, and this reducing agent has one purpose in life, and that's this reaction as far as we are concerned. Now notice this reducing agent is similar to this, okay, and it doesn't matter where you put the hydrogen. Some people put the hydrogen here and some people put the hydrogen on this side. It makes no difference. I do it both ways. In my notes, I actually left it off, okay, on page 2. But notice this reagent is very similar to this reagent, except 3 of the hydrogens have been replaced by OT butyl groups. By replacing those with OT butyl groups, this reducing agent is a weaker reducing agent than the top one. So it doesn't take the compound all the way to the alcohol. It stops the reaction at the aldehyde. So notice this series of reagents. If I take a carboxylic acid, and in step 1, I treat it with SOCl2, and then step 2, I treat it with this reducing agent. The product is going to be an aldehyde. This is one of the few ways that you can take a carboxylic acid and stop at the aldehyde, because most reagents that are strong enough to change it to the aldehyde are also strong enough to take the aldehyde and turn it into the alcohol. So if you want to turn a carboxylic acid into an aldehyde, this is a very easy way to do this. Treat it 1 with SOCl2 and 2 with this reducing agent. Okay? So again, when you make your note card out, you could make the note card with the individual reactions, but these two reactions are oftentimes used together, and it's the only way to turn a carboxylic acid into an aldehyde that we know of. So again, you have all these on your note cards. Now, we've already seen this reaction before. Okay, if we take an acid chloride, we saw this reaction back in the chapter on, I forget which chapter it was, but we saw this reaction when we were talking about granular reagents, and treat it with a cuprate agent. And a cuprate agent is also called a Gilman reagent. So notice it's just a R2CuLi. This is called a cuprate. What ends up happening is the chloride is replaced with an R group from the cuprate reagent. Okay? Another way to write this is to do this. In step 1, we just take and make this set of reagents. because this is how you make a cuprate. You take a lithium reagent and react it with copper iodide. Okay, so this set of reagents means the same thing as this. I can either give you the cuprate or I could give you the lithium reagent with the copper iodide. Both of these mean the same thing. This is just the way to prepare the cuprate. So on the test, I could give you this question. So what's going to happen? Okay, and if I put a 2 in front of there, just to make it balance. Notice this is my R prime, this is my R. So what's going to happen? The methyl group is going to replace the chlorine group. So what would be the product of that reaction? Okay, so that's another way to take a chloride and turn it into a ketone. So if you look on page 2, we can take carboxylic acids and turn it into aldehydes. We can take acid chlorides and turn into either aldehydes or ketones. Okay, so we have 2 different reactions. Again, new ways to make aldehydes and ketones. Now what we're going to do in the rest of this section on chapters 3, 4, on pages 3 and 4, is we're going to look at reactions of the aldehydes and ketones. And basically the aldehydes and the ketones are compounds that have a C double bond O. And that C double bond O can be backside attacked by a nucleophile. That's basically what the Grignard reactions are. That's basically what most reactions of aldehydes and ketones are. So if we had a ketone or an aldehyde, I'm illustrating this with a ketone, okay, and we attack it with a nucleophile. The nucleophile is going to do a backside attack and kick that pair of electrons up. That's what always happens. The nucleophile attaches to the carbon, making the oxygen negatively charged. Then if we protonate this in step 2, remember all protonation does is protonates the oxygen. So notice what we have. We have taken a ketone and turned it into some type of alcohol where we have done our backside attack with the nucleophile. Okay, that's all there is to this. Notice the reaction that I'm using on page 3 in the notes is just where I'm using a Grignard reagent as my nucleophile. Remember, Grignard reagents are nucleophiles because they have a negative charge. So if I gave you this question on the test, I would expect you to be able to give me the product. So this would be a typical test question. And notice how I write this sometimes. I write, that's step 1. Step 2 is just acidification. So if I gave that to you on the test, I would expect you to be able to work the problem. Again, notice how I do this. I always, whenever I'm doing reactions, I always follow the flow of the electrons. Don't try to just look at the notes and picture it. I mean, that's what you have. You have in your notes that this does a backside attack, but then actually do the backside attack, kicking that pair of electrons up. Notice whenever I write it, I don't try to move everything around. I just leave things where they are. That backside is attacked, kick the pair of electrons up, and notice what I get out of this. In the next step, all the acidification does is protonates the alcohol. So again, it's not going to always be an alcohol, but in this case it was. Why? Because I used a Grignard reagent. Now the reaction on page 4. Notice that this was an attack by a nucleophile, a negatively charged species. I want you to look at this entire mechanism before I erase it. In none of my steps was my organic compound protonated. It can't become protonated if it's in until we add the H plus. None of the steps can have a positively charged species because you can't have a positively charged species present when you have a Grignard reagent. On page 4, we're going to look at a different mechanism. And this is whenever we're using a nucleophile that is not negative. It's in acidic solution, but it's still a nucleophilic attack. Watch what happens. If we have a ketone and it's in acidic solution, what do you think that acid is going to do? What do acids always do? They protonate things. Now, because this is protonated, we can draw a resonance structure for this. Now, it's not a good resonance structure, but it is a resonance structure. Notice we can bring this pair of electrons up onto the oxygen. Okay, when I do that, notice this carbon becomes positive. Because of that resonance structure, the carbonyl can even be attacked in acidic solutions, even though you're going to be using a weak nucleophile because it can't be negatively charged in acidic solutions. The carbon is positively charged, which means it's more susceptible to attack, and therefore even a weak nucleophile can come and attack it. So let's look at an example of that. If we take this compound here, benzaldehyde, and we were to treat it with HCN. Now, HCN is an acid. So what's the first step? The oxygen becomes protonated, followed by the backside of attack of the CN minus, because remember, if HCN is in there, it's a weak acid which breaks apart partially into H pluses and CN minuses. So it comes in here, kicking out that pair of electrons again, okay, to give me this compound here. Now notice in this case, we're protonated because the hydrogen was already there. Now in a reaction that we have not seen yet, we're going to learn how to take this molecule and we're going to add glucose to it, just simple sugar, glucose. And what happens is the glucose replaces that H. Now, we haven't seen that reaction yet, but we will see it shortly, okay, in a chapter coming up soon. And what that does is put a glucose molecule in place of that H on the alcohol. Okay? Now, this compound has a name. It's called Laetril, Laetril. Now, if you have your phone with you, what I want you to do now is get on your search engine and type in Laetril, Chad Green, and you probably won't have to type in anything else. You could type in Laetril, cancer, leukemia, Chad Green, death, okay? But Laetril and Chad Green. Now, Laetril is a drug. While you're doing that Google search, I'll just talk a little bit about this drug. Laetril is a drug that in the early 1970s was used to treat cancer, but it was illegal in the United States. And Chad Green had leukemia. His parents took him to the doctor. The doctor said, "I'm sorry, your son's going to die. There's nothing we can do. Take him home, love him, spend whatever time you've got left with him. We're sorry." Well, they had heard of this experimental cancer treatment called Laetril, and it was available in Mexico, and they took him to Mexico to be treated. Unfortunately, he died while given the treatments. Notice the treatment adds cyanide. These compounds break apart in your body, this drug does, to produce cyanide in your body. And what you're hoping is the cyanide, which is toxic, kills the cancer before it kills the person. I mean, that's the way most cancer treatments work. The chemotherapy is toxic, but it hopefully kills the cancer before it kills the patient. And Laetril is nothing but a chemotherapy treatment. Well, whenever his parents came back into the United States, they faced all kinds of legal battles and everything for taking their son out of the country to be treated. And of course, the treatment killed him. And it was one of the most publicized cases dealing with this drug Laetril. Later on, there was another case that came up with Laetril. Now, this is a case of somebody you might know or might not. The guy's name is Steve McQueen, okay? And he's a famous actor, okay? Starred in movies like The Great Escape, Bullet, several other movies. He always drove fast cars and motorcycles in all of his movies. And he was the handsome, movie star type and everything that all the girls went goo-goo-eyed over and everything. And he had a cancer. I think he had pancreatic cancer and went out of the country to be treated. And unfortunately, he died from this treatment also. But Laetril now is still illegal in the United States. But you can buy Laetril. Okay, it's isolated from apricot seeds or apple seeds. So if you take an apricot and you crack open the hard seed and you get that juicy middle in the middle of it, it's got Laetril in it. Okay, apple seeds have a small amount. You can actually buy this compound, okay, and use it, and it's sold as a cancer preventative. And it's sold under the name vitamin B17. Vitamin B17. If you take this extract, which has cyanide in it, and you take it daily, and you were to start developing a cancer, now this is what the treatment claims, and you were to start having a cancer form in your body, having this vitamin B17, this Laetril in your body, does what? Kills the cancer before it has a chance to grow. Okay, so it's a cancer preventative. If you have cancer, there's treatment options where you take this in higher doses and it kills the cancer and everything. I'm not a proponent for it. I'm not an opponent for it. But if you if you're going into a health field and you just want something that's really fascinating, then you can be careful with this, because you can go down a rabbit hole and spend hours just reading article after article after article on how this vitamin B17. I think it also goes by the name, and I'm not certain if this is the right thing. It's been so long since I've read this. PQQ or PPQ, PQQ or PPQ, I think is the other name. Hold on just a second, and I will look at that. I've got a reference for it somewhere. Let me find that. Again, I read all this stuff and then I forget the details of some of the articles. Give me just 1 second. I should have already have done this before class. Yeah, it's PQQ. Okay, PQQ is the other name that this goes by, PQQ. So if you look up this, I mean, it's fascinating. For those of y'all who believe in alternative medicine, I know some of y'all are thinking about going to med school. Some of y'all may be thinking about going to a school where holistic medicine is taught as a class and everything. But it's a really fascinating discussion. And again, if you go to the sites where they're trying to sell you this, obviously you hear all these wonderful things, but there are actually a lot of good sites out there that you can go to where they give you a good medical discussion of this. But notice this drug is simply made by taking benzaldehyde, treating with hydrogen cyanide, then treating that with glucose to make this drug. Now, how many apple seeds, if you were to eat apple seeds, or how many apricot seeds do you need to eat to get enough of the drug in your system? Again, it's probably talked about in some of those articles. But these supplements are, they're sold as a supplement in the United States. Therefore, they're not regulated by the FDA. So therefore, they can sell it as a supplement and bypass any kind of regulations. But again, a very, very interesting article on the drug Laetrile and the side effects of it. And you'll hear some of these people who swear that the doctor had given them no chance of living, and then they took this drug and were completely healed. And then you'll hear other people say that the drug done nothing for them. And then you'll hear others say that, it was a detriment to them and everything. But again, for those of y'all who are going into a medical field, this is a very, very controversial issue. And it's risen back up now that this supplement, and it's called vitamin B17 or PQQ. And the articles are really pretty interesting. Okay, so let's get on with the rest of the lecture. Though we've got one more reaction. Now, I remember when I had this reaction, and it's on page 5 in part 2 of the notes, in organic chemistry. I really never really understood what was happening. First of all, how would you pronounce that name? Wittig. Some people will pronounce it as the Wittig reaction, and some will pronounce it as the Wittig reaction. Obviously, this is a German chemist, and oftentimes they pronounce their W's as V's. I'll pronounce it as the Wittig reaction. Okay, here's what happens in the reaction. I'm going to give you the easy way to remember this reaction. Then we're going to talk about what actually happens. In this reaction, what happens is you take an alkyl halide and you react it with a ketone, and you get an alkene. So watch how I'm going to write this reaction. I'm going to write my alkyl halide. Now watch what I'm going to do. I'm going to write it like this. And I'm going to write my ketone like this. Okay? What happens, and this is not the way it happens, this is the overall result of this reaction. These atoms go away, and you get an alkene. Okay? So, this is the Wittig reaction. It's a way of coupling two carbons together to form an alkene. So just bear with me for a second. That's the overall result. Now let's look at what happens. Okay? And then I'm going to give you the way you need to write this on your note card. I would write it on my note card this way here, for one, because that gives you, if I give you the two compounds, you can easily predict what the product of the reaction is. But here's what happens. We're going to take this compound here, a phosphorus with 3 phenyl groups on it. Now, a phosphorus with 3 phenyl groups on it, since phosphorus is in group 5, still has a lone pair. Although this is very, very bulky, it is still a good nucleophile. So if I react this with an alkyl halide, okay, so I'm going to write my alkyl halide here with my R group, my H, and my H, and my halogen on here. This is a nucleophile and does a backside attack to kick the halide off. That's the first step in this reaction. Now, don't make this any harder than it is. Once I finally figured it out, it wasn't bad, but until I figured out what was going on here, it was hard to see what's going on. This is just an SN2 reaction. Okay, this is just an SN2 backside attack. So what I end up with is something that looks like this. Notice I get inversion, so if this were chiral, it would stay chiral. Okay, so I get this with the triphenylphosphine group attached here. Now I'm going to write the phenyl groups with a little circle with a line through it just because I get lazy when I do this. So I'm going to just write the phenyl groups like that. It turns out that if we treat this with a lithium reagent, and the lithium reagent we're going to use is this. Four carbons in the row. This is called N-butyl lithium. Okay, because this is a butyl group. Now, all we need to know about this is that this is going to pull off a hydrogen because this is negative and this is positive. This comes in and pulls off one of these hydrogens, forming this compound here. Now, bear with me as I write this. Now, the reason this reaction works is because phosphorus likes to have 5 things around it. If I look at this right here, notice this phosphorus is positively charged. Remember, phosphorus is in the same group as nitrogen. If you look at this, this phosphorus has 5 total bonds around it, but that's okay. Phosphorus can have 5 bonds around it. So the first step was just an SN2 backside attack treated with N-butyl lithium to pull off one of the hydrogens to form this. Now this compound has a resonance structure in it, and it's shown in the notes. We can take this and rewrite it using resonance like this. Now just pay attention because this is not hard. It all makes perfect sense if you take your time and follow it slowly. Moving this pair of electrons over to the carbon atom, we get a pair of electrons on the carbon, so the carbon becomes negative and this becomes positive. Okay? This is a resonance structure, but it's an important resonance structure because now notice the carbon atom has a negative charge on it. So this whole process was to be able to give this carbon a negative charge. Notice the carbon went from partially positive to partially negative. Now this negative charge then can react with, I'm just using R's and R double primes. It comes in and does a backside attack, kicking off the oxygen. Okay. Now I'm out of room on my board, so I'm going to have to erase some of this. I was hoping to be able, well, let me see, I might be able to get the rest of this on here. Notice what this now gives me. An R hooked to a C, let me say an R prime hooked to a C, hooked to an R double prime with an oxygen on it, with a negative charge, hooked to a carbon, which is hooked to a hydrogen, which is hooked to an R, with a triphenyl group over here, hooked to a phosphorus. And the phosphorus is positive charge. Then these two pieces get together and leave, taking this pair of electrons down, forming the double bond. So notice the mechanism. Now let me go through this again. This reacts with the alkyl halide in a backside attack to form this. This gets deprotonated by the N-butyl lithium to form this, which is basically a positive and a negative charge here. The negative comes in backside attacks, kicking the oxygen off, and then the positive and negative get together and leave. Okay? Now, the key step in this reaction, and this is what you have to realize, is this step here, the SN2 step. For this reaction to occur, this must backside attack here, which means the alkyl halide has to be either primary or secondary. Okay? And it has to have a hydrogen on it over here that can be lost. So the alkyl halide that you start with has to be primary or secondary. Now, that's the Wittig reaction. There's two questions that I can give you on the test. I can give you the reaction and ask you to predict the products. Or I can give you the product and ask you to predict the reactants. Now, I don't have an example in my notes where I'm going to give you the way the reaction would be worded on the test. So you need to add this one to the top of page 18, or page 6 rather, on part 2. Suppose I gave you this reaction. And I'm going to use that abbreviation for my triphenyl phosphine. I could have given you the phenyl group, but sometimes I'm lazy and I write that, and I could do that on the test. Step 2 is treatment with N-butyl lithium. Step 3 is treatment with some ketone. And I'm going to ask you, what's the product of that reaction? Okay. Now, if I give it to you this way, We'll go through the steps in just a minute. Here's what I would do. First of all, I would recognize that this is the Wittig reaction, because this and this are the first two steps in the Wittig reaction. So what I would have done is I would have redrawn my alkyl halide. Now notice when I redraw it, I put the halogen and the hydrogen on the inside. I would have redrawn my ketone. Now notice whenever I put and redraw the ketone, I put the oxygen on the inside. And here's the overall result. Those atoms go away. So if I give you the reaction like this, it's easy to predict the product. So notice the product. With an aromatic ring up here and a CH3 down here. So if I give you this way, there's what happens. Now notice that's the product, okay? Now we're going to actually see how this reaction occurs. So step one is what? We take this and treat it with the triphenyl phosphine. So what happens in this step? Backside attack kicking off the chlorine. So we get a CH, H, H with the triphenyl phosphine group attached. Okay, it's kicked off the chlorine. SN2 backside attack. Step two was treatment with N-butyl lithium. Remember what that did? That pulled off that hydrogen. Okay, so that gave me this, which we can rethink of as being this. Remember, that was the resonance structure we drew. Now I'm going to draw the ketone underneath this now. And I'm going to put the C with the methyl group here and the phenyl group over here. And then I'm going to put my double bond O here. Now I drew it in this orientation because notice this carbon is negative and this carbon phosphorus is oxygen. This carbon is negative, this phosphorus is positive. This carbon is partially positive and this oxygen is partially negative. And watch what happens. This pair of electrons goes there. This pair of electrons goes there. What this now gives me is, let me redraw the structure, gives me temporarily something that looks like this. Okay, and the phosphorus again has the three phenyl groups on it. Now we're going to just do the electrons again. And notice what that gives me. The phosphorus with the triphenyl phosphorus now becomes attached to the oxygen. And notice what we get here, the double bond. Now this really is only useful when one of the carbons is symmetrical. Otherwise, we would get both cis and trans out of the products. So one of the carbons has to have two atoms that are the same or two groups of atoms that are the same. So notice if I give you this, it's easy to predict the products, or you can go through the steps and predict them. Now, if I do this the other way, and I just asked you this question, using the Wittig reaction, let's make this compound. So this is the other way I can give you this question on the test. How do you make that compound using the Wittig reaction? Okay, there's two options. Now notice the two options. Now, I'm just going to break it apart first. So if I took this piece and then, let's see, the way I've been doing this is I put the H and the Cl here, and this is my ketone. Do you agree that if I remove those atoms, I would get that product? The other choice is to let this be the alkyl halide and this be the ketone. So notice I wrote it both ways. Now I have to ask myself, which one of these is better? Notice this is a secondary alkyl halide. This is a methyl alkyl halide. It's least substituted. This one is going to be the best one for the SN2 product. So I now know that this is my reaction. So if I were to give you this on the test, I would expect you to say CH3Cl. Step 1 is going to be what? The triphenylphosphine. Step 2 is going to be the N-butyl lithium. And these are always going to be the first two steps in this Wittig reaction. And step 3 is, what ketone do I now need to react that with? And now notice step 3 is simply this. So in the Wittig reaction, if I give you the product, there is going to be two choices. One of them will be a better choice than the other. And what decides which one is the best choice or the better choice is which one of the two halides, this one or this one, is better in an SN2 reaction. And remember, the least hindered the halide is, the better the reaction is in an SN2 reaction. So that's the last question that's going to be on the test. And again, I'm looking at your sample test, or the last question out of this section on the sample test. And it looks like there is a Wittig reaction on the test. Okay. Now that finishes up section 2.